Hi, y'all. Hope you're doing well. Today we're going to talk about difference equations and the Fibonacci sequence as sort of an application for how the ideas of diagonalization and eigenvalues can be very useful in a place where it might not seem obvious that they should be very useful. Okay? So we're going to define the Fibonacci sequence, maybe the most famous sequence of numbers of all time. So let's define the Fibonacci sequence recursively. Sorry. There we go. We're going to define it recursively as follows. F0 is going to be 0. F1 is 1. And for every k bigger than or equal to 2, we're going to define f sub k as f sub k minus 1 plus f sub k minus 2. Okay, so the way that you get the Fibonacci sequence is you start with 0 and 1. That's the most classical thing. And then for each term, you add up the previous two terms, right? So if I were to list the first few terms of the Fibonacci sequence, it starts with 0 and 1. Then f2 is f1 plus f0. So that's 1 plus 0, that's 1. f3 is f2 plus f1. f4 is f3 plus f2. f5 is f4 plus f3, so it's 5. f6 is 8. f7 is 13. f8 is 21, ... Okay? So you can compute however far out you want by adding the previous two terms. Okay, and the Fibonacci sequence arises very frequently in nature because it's defined by such a simple formula, right? So if you are talking about the number of rabbits in a field, which I think is Fibonacci's original motivation, you start with one pair of rabbits in a field. Let's assume, by the way, that our rabbits reproduce once a month, or maybe it's once a year. Let's say once a year, and it takes 1 year to get to reproductive maturity, and let's assume that our rabbits never die. Okay, so if you start with one pair of rabbits, a male and a female, then at the end of the first month, there's still one pair of rabbits because they've now reached reproductive maturity, and then they reproduce, right? At the end of the next month, you have your original pair, right? So this was like we started with one pair of rabbits. At the end of the next month, there's still one pair of rabbits. Then at the end of the next month, they reproduce. Sorry, what the rabbits that they reproduce with the reproduction from the previous month yields another pair of baby rabbits. So now at the end of that month, there's two pairs of rabbits. And the original pair reproduces at the end of that month, but the newborn pair needs to wait a month to reach reproductive maturity, right? So that means that at the end of the next month, the original pair has had another pair of rabbits, and there's also the first pair that they had, which have now reached reproductive maturity, so we're at 3 pairs of rabbits. But now we have 2 pairs of rabbits at reproductive maturity, so they'll produce 2 new pairs of rabbits by the end of the next month. So you have 5 pairs of rabbits, and basically you can, because of this delay of 1 month to reach reproductive maturity, you have to add up the number of rabbits you had in the previous step plus the number of rabbits you had in the step before that. Okay, so you could also count the number of ancestors of a bee by the Fibonacci sequence just because it's such a simple recurrence. Now, this Fibonacci sequence doesn't seem to involve any linear algebra, any diagonalization, any eigenvalues at all, but there's a nice way for us to understand this using linear algebra. Okay, so if you want to compute, if I asked you to compute f100, then the naive approach is just to continue adding, right? So f9 is 34, then f10 is 55, f6 is 89. Sorry, did I say f6? f11? See, I'm already confused because adding up those numbers one at a time, if you made a mistake somewhere along the way, that's kind of bad, right? And you'd have to do at least, I don't know, 100 operations, right? But we can inject a little linear algebra into this by defining wk to be fk plus 1 fk. Okay, so what I'm going to do is I'm going to track 2 consecutive Fibonacci numbers in a single vector. And the good thing about this is that the next Fibonacci number only depends on these 2 Fibonacci numbers, right? fk plus 2 only depends on fk and fk plus 1. So wk plus 1, right, is fk plus 2, fk plus 1, etc. And the thing to notice here is that wk plus 1 is equal to the following matrix, 1, 1, 1, 0, times wk. Okay, why is this? Let me just do the multiplication for you so you can see why. Right, if you do this multiplication, what do you get? In the first coordinate, you get fk plus 1 plus fk. And in the second coordinate, you get fk plus 1. But of course, this is just fk plus 2. So if we keep track of the data of two consecutive Fibonacci numbers in a vector, then if you multiply by this matrix, it takes you from one vector to the next vector. Okay, so what is our initial state? So we start with w naught, right? This is f1 comma f0, which we said is just 1, 0. But now you multiply by a. Let me write this matrix A back here again. A w naught, that's the same thing as w1. And w2 is a w1, but that's a times a w naught. That's a squared w naught. Right? In other words, if you continue this process, w to the k is a to the k, sorry, w sub k is a to the k w naught. So if you want to understand the 100th Fibonacci number, well, you could instead understand this vector w100, which is the 101st Fibonacci number, comma the 100th Fibonacci number. So if you could understand this vector, you'd understand the 100th Fibonacci number. And this is just a to the 100 times w naught. And we just saw in the previous section, the previous chapter, that computing the large powers of a matrix is somewhat easy if you can diagonalize it. So this would be easy, at least somewhat easy, if we could diagonalize. Because if we could diagonalize, then I could actually just do this computation because I could raise the diagonal matrix to the 100th power. That's probably pretty easy. I could do that with a calculator, say, right? I could compute I compute u inverse, and I could multiply out. Whereas even if I gave you a calculator, still adding up the numbers to get to f100 is probably going to be pretty tricky, right? Okay, so let's try to diagonalize. So what do you do? The first thing you do is you try to find the eigenvalues using the characteristic polynomial. So the determinant of a minus ti is the determinant of this matrix, negative t, right? Which is 1 minus t times negative t minus 1. So that's aka t squared minus t minus 1. Okay, that's the characteristic polynomial. To find the eigenvalues, you want to find the roots. So what are the roots? This is a quadratic polynomial. So to find the roots, we could use the quadratic formula, right? So the roots are given by 1 plus or minus root b squared, which is 1 minus 4ac, which is plus 4 over 2. So it's 1 plus or minus root 5 over 2. Okay, so let's call the positive 1, lambda 1, and let's call the negative 1, lambda 2. And this thing is approximately 1.618 something. This one is approximately negative 0.618 something. Okay, and by the way, this thing is what's called the golden ratio. So the golden ratio appears lots of places in nature, and that's because it's related to the Fibonacci sequence, essentially. That's my opinion anyway. Whenever I see these sort of like pop math articles about the Fibonacci sequence and the golden ratio, basically the reason is because the Fibonacci sequence occurs so fundamentally because of its simple definition, and the golden ratio is intimately tied to the Fibonacci sequence. Okay, well, these are the eigenvalues, right? Now I need to find eigenvectors by taking the null space of a minus this eigenvalue I. So let me just show you what that is, right? It's 1 minus lambda 1, 1, 1, negative lambda 1. And you can compute that this thing is spanned by the vector lambda 1, 1. So let's call this vector u1. It's just the golden ratio, comma 1. And you can check that the second eigenspace is the span of the vector lambda 2, comma 1. So let's call this vector u2. Okay, I've used the shorthand lambda 1 and lambda 2 because I don't want to keep writing 1 plus root 5 over 2, but it's just a number, right? So in principle, if you want to compute with this, it's just a number. Okay, now that means that we had two distinct eigenvalues, so the matrix is in fact diagonalizable. So what you can do is you can take u to be this vector and this vector, so this matrix. You can take lambda to be the diagonal matrix of eigenvalues, and then A is u lambda u inverse. Right? So if you are interested in F100, then you can instead compute W100. So Wk in general is a to the k W naught, which is u lambda to the k u inverse W naught. So if you, this particular example of F100, this is just a to the 100 W naught, right? So it's u, and then this first eigenvalue to the 100, this second eigenvalue to the 100, times u inverse times 1, 0. Okay, and this thing is actually computable by you. You could compute this just by just with a calculator. You could do this, right? So we now have an example where at the start it wasn't clear that linear algebra, I mean, if I just define the Fibonacci sequence, you don't even know any linear algebra to understand this, how the sequence is defined. But it turns out that if you use a little of linear algebra, it turns out that knowing the eigenvalues and eigenvectors of a certain matrix becomes very useful. Okay, so we can even talk a bit more generally to try to understand a little bit better, right? So what I'm going to say next holds not just for the Fibonacci sequence, but in general. And then we'll return back to the Fibonacci sequence. Okay, so here's the general setting. And to understand this, first thing we want to do is we want to make sure that we understand matrix vector multiplication from Math 308, which very few people do when they first take Math 308. Okay, so let's let A be any m by n matrix, m rows and n columns. And, right, so A has m rows and n columns. But let's name the columns A1 up through AN. So these are the columns. And let's also give the rows a name. So I'm going to call this B1 transpose because it's going to be a row vector. So think of B1 as a column vector, and I've just transposed it so that it's a row. So let's give these names. So there's M row vectors like this, okay? Now, a very fundamental fact from Math 308 is that if you multiply a matrix times a vector, the result is a linear combination of the columns of the matrix. Go back and look at your 308 notes. Your professor said it and wrote it down, I promise. I definitely say it when I teach my class. If you take the vector x to be x1, x2 up through xn, then A times x you can think of as a linear combination of the columns of A, namely x1 a1 plus x2 a2 plus xn an. So if you multiply this matrix by a vector, you take the linear combination of the columns, where the vector tells you the weights that you take for each column vector. Okay, another thing that's very useful is, right, so this thing is a vector in Rm, as it should be, right, because the matrix is m tall. If you want to understand the ith coordinate of the vector, it turns out that this is the same thing as the ith row multiplied by the vector x, which is, that's exactly how you compute the product, right? If I asked you, well, what happens in the very first, what happens in the top of the vector ax, right? I'm going to write a like this. Bm transpose times x. Exactly what you would do is you would take this first row and you would dot it with this row vector. In other words, it's like you would multiply this matrix by this vector. So two very useful facts. If you multiply a matrix by a vector, what you get is you get a linear combination of the columns of the matrix. And if you're interested in just the ith coordinate, you can just essentially dot a row with the vector. That's the same thing as a matrix multiplication, as long as you take the dimensions of your matrices to be the correct size. Okay, there's also a corresponding version on the left. So this is like you multiply a matrix by a row vector on the right. There's also a corresponding thing on the left. So if y is a vector in Rm now, so x was a vector in Rn, then we can consider y transpose. This is a vector that looks like this, y1, y2. It's like a row like this, right? And this thing you could multiply on the left by a, right? Because this thing is 1 by m. This thing is 1 by m, and a is m by n. And so the result that you get would be a 1 by n vector. And it turns out that this thing, if you take the transpose, if you take a row vector on the left times a, what you get is you get a linear combination of the rows of a. So this thing is exactly y1 b1 transpose plus dot 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 plus ym bm transpose. And if you're just interested in the jth component, it's y transpose times multiplied by the jth column vector. Okay, so this is just a genuinely useful thing. There's also, going along with this, the definitions of the column space and the row space. Right, so the point is that the column space is defined to be the span of the columns of A, but you can get any linear combination of the columns of A by multiplying by some vector x. So every single linear combination of the columns of A is given by A times some vector x. And so the span of the columns is the same thing as every possible A times x. Okay, so that's the next sort of result in the this is like a definition / theorem, right? So if A is an n by n m by n matrix, then the column space of A is defined to be the span of the columns. Let me just use the same notation as in the previous slide. Sorry, there's n columns, but this is the same thing as every possible A times x where x is an Rn. This is a subset of Rm. Another way that you learn this in Math 308 is that the column space of A is the same thing as the range of the linear transformation given by multiplication by A. If you look at all possible things that you can get after you multiply by A, that's the same thing as the column space. And the row space of A, which is defined to be the span of the columns, the span of the rows of A, I guess maybe the transposed rows. That's the same thing as all possible y transpose A's, where y is an Rm, and this thing is a subset of Rn. Okay. So now, let's go back to difference equations. Okay, so back to difference equations. Sorry, I have notifications muted. I don't know if you can hear my phone buzzing. Maybe you can't. I have notifications muted, but when I have the screen open, it doesn't mute them. Okay, so suppose a matrix... Okay, so back to difference equations, right? We're now going to call our vectors W, we're going to call them state vectors. Okay, so let's call the WK the kth state vector. So we imagine we have W0, W1, W2, ... And these represent some information, like, for example, the 0th or the kth and the k plus first Fibonacci number. But these could track anything, but for our example, they were the k and the k plus first Fibonacci number. And let's suppose that there exists a matrix A such that, like, to get to the kth state, you can just multiply a to the k by w naught. In other words, suppose you have a matrix that takes you from one state vector to the next. This is the same thing as a times wk equals wk plus 1. So you have a matrix that transitions you from one state to the next. Okay, so this is the same. This is a more general setup because I'm not assuming that I'm using the Fibonacci numbers here. All I'm assuming is that I have some process where I have a vector of data, and multiplying by my matrix A takes me sort of from one state to the next state, and then I multiply by the same matrix A to take me to the next state. Okay, what we saw is that if A is diagonalizable via A equals U lambda U inverse, then if you want to understand the kth state, you just need to diagonalize the matrix and multiply it by the initial state. Okay, now what we're going to do is we're going to do the following. Let C be U inverse of W naught. This is really just changing basis to the basis of eigenvectors of the matrix. So this gives you the coordinates of W naught with respect to the eigenbasis of A. And you can actually solve for C, because C, it's the solution to U times X equals W naught. Right? C is the thing that solves for this. U times C is W naught because you can multiply the left by U. Okay, but now let me do a little bit of linear algebra magic. The kth state vector we said was U lambda to the k U inverse W naught. But we just called U inverse W naught, we called that thing C. And it's a vector that we can actually solve for. So this is U lambda to the k C. Now let's write out what this is. Suppose the columns of U I call U1 through UN. Lambda to the k is, of course, just this diagonal matrix. And let's call this vector C1 up through Cn, right? That's the coordinates of the initial state vector in terms of our eigenbasis. Well, this multiplication on the left here, this is easy to do because it's a diagonal matrix. So this is this matrix, again, those are the columns, times lambda 1 to the k C1 down to lambda k to the n Cn. That's how you do a multiplication by a diagonal matrix. But now I use the fact that multiplying a matrix by a vector just gives you a linear combination of the columns of the matrix, right? So this thing is just lambda 1 to the k C1 U1 plus lambda 2 to the k C2 U2 plus lambda n to the k Cn Un. Okay, well, what does this mean? Again, you can, if I give you the matrix A and you can diagonalize it, you can find a basis of eigenvectors, and you can actually compute this vector C just by changing basis to the eigenbasis. And what this is saying is that the kth state is given by just an easily computable linear combination of the eigenvectors of A. The kth state is given by an easily computable linear combination of the eigenvectors of A. Okay, so let me write this down as a theorem, because we'll see very shortly when we study Markov processes how useful this is. So suppose that for every k, the way to get from one state to the next is to multiply by this matrix A with initial state vector W naught. So then if A is diagonalizable with basis of eigenvectors given by u1 up through un, with eigenvalues lambda 1 up through lambda n, then the kth state is given by c1 lambda 1 to the k u1 plus cn lambda n to the k un, just the sum of these ci lambda I to the k ui, where c is just this given by u inverse w naught. Okay. Now, why did I bother doing this? The reason why I bothered doing this is because if you look at this equation, as k gets very large, some of these terms will matter more than others. Because what you're doing is you're taking a power of the eigenvalue. That means if there was like an eigenvalue that was very close to 0, say, as you take a higher and higher k, that eigenvalue to the k gets very close to 0 and doesn't really contribute to this sum very much. And in fact, the bigger the eigenvalue is, the more it matters for k growing large. In other words, the long-term behavior depends on the large eigenvalues. So the long-term behavior of this sequence of states depends mostly on the large eigenvalues of A. Okay, this is actually a very, very deep insight, and it's not at all obvious if you didn't do any linear algebra. If I asked you about the long-term behavior of the Fibonacci sequence, I don't think any of you at the beginning of this lecture would say, oh, well, it really deeply depends on the eigenvalues of this particular matrix. But it turns out that it really does. Okay, so let's go back to the Fibonacci sequence. Let's apply this theorem to the Fibonacci sequence. So back to Fibonacci. Right, so we said that u was lambda 1, 1, lambda 2, 1, right? Lambda was just lambda 1, lambda 2, like this, where lambda 1 was 1 plus root 5 over 2, that's the golden ratio, and lambda 2 was 1 minus root 5 over 2, that's negative of the golden ratio minus 1, essentially. Now our initial state was w naught, was 1, 0, and we can just solve uc equals w naught, right, by augmenting this thing, say, or by using a computer. And we could actually compute that c is equal to 1 over lambda 1 minus lambda 2, negative 1 over lambda 1 minus lambda 2. It's kind of a reasonably nice vector. Okay, and you can, I mean, this is a thing that you could actually check. You just check to make sure that these are the coordinates of 1, 0 with respect to the eigenbasis. Okay, you can actually check this. Therefore, the kth state is given by, what was it? It was c1 lambda 1 to the k u1 plus c2 lambda 2 to the k u2. That's what our formula was. It's a linear combination of the eigenvectors of A What is C1? C1 is 1 over lambda 1 minus lambda 2 times lambda 1 to the k times U1, which is lambda 1, 1, plus C2, which was negative 1 over lambda 1 minus lambda 2 times lambda 2 to the k times lambda 2, 1. Okay, now from this, we can actually compute the kth Fibonacci number, because the kth Fibonacci number is just the second coordinate of WK, right? So this thing is FK plus 1 FK. So this means that, what is FK? I just need to look at what would I get in the second coordinate, right? So from the first one, what do I get in the second coordinate? I get this coefficient times 1. So it's lambda 1 to the k over lambda 1 minus lambda 2 times 1. And in the second coordinate here, I get this coefficient times 1. So it's actually lambda 1 to the k minus lambda 2 to the k over lambda 1 minus lambda 2. Okay, so this actually gives us a closed form solution for the kth Fibonacci number. Now you could definitely compute the kth Fibonacci number, because this thing you can actually just plug into a calculator in like 30 seconds. I guess 1 plus root 5 over 2 is not the nicest thing. But this is a highly non-obvious closed form solution to the kth term of the Fibonacci sequence. Okay, and what happens to k in the long, what happens to wk in the long run, or in other words, what happens to fk in the long run? In the long run, the thing that really matters, right? So, okay, in the long run, in other words, as k tends to infinity, again, wk was c1 lambda 1 to the k u1 plus c2 lambda 2 to the k u2. But remember that lambda 2 is negative 0.618, whatever. So if you raise it to a very high power, it gets very close to 0. So in the long run, you can ignore this lambda 2 to the k term. By ignore, I mean it matters less and less and less. So really, in the long run, as k tends to infinity, fk tends to, or fk is really approximately lambda 1 to the k over lambda 1 minus lambda 2. So it's approximately 1 over root 5 times 1 plus root 5 over 2 to the k. So if you just want to approximate the Fibonacci numbers, it's even easier. You just raise a single number to the kth power and multiply by 1 over root 5. And again, the point to note here is that the long-term behavior really only depends upon the largest eigenvalue. That doesn't sound that deep, but it turns out that has a lot of really important consequences. Where you can, because a matrix, a huge matrix, is an extremely hard thing to understand, right? If I give you any matrix that people actually work with in the real world, right? Like the Facebook friend graph, you make the adjacency matrix. This is a graph that's, it's a graph with like billions or hundreds of millions of nodes. That means that the matrix is like 100 million by 100 million. But it turns out you can understand some amount of it by just understanding what are the largest eigenvalues. And those are just numbers. You don't no longer need to worry about a 100 million by 100 million size matrix. Okay, and let me just point out, because it's mentioned in the notes, also, if you take the limit as k goes to infinity of the ratio of the Fibonacci numbers, okay, so let's do some experimentation. So the Fibonacci sequence was 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. So I'm asking, what happens if you take the next Fibonacci number over the previous one, right? So first you would have 1 over 1, that's 1. Then you'd get 2 over 1, that's 2. 3 over 2, that's 1.5. 5 over 3, that's like 1.666. 8 over 5, that's 1.625. 13 over 8, now Sorry, that's not 1 point. This is 1.6. 13 over 8 is 1.625. And then 21 over 13 is something, but it's approximately 1.6 something. Somehow the ratio of the Fibonacci numbers seems like it's tending to something. And it turns out that it tends to the golden ratio. And actually, this you can prove without linear algebra. All you do is you just assume that it has a limit. So if you assume, okay, yeah, it tends to the golden ratio, but if you assume that the limit is equal to L, then also it would have to be the limit of the k plus second over the k plus first. Oh, sorry, let me do it like this. Fk plus 1 over fk is the same thing as fk plus fk minus 1 over fk. That's by the definition of the Fibonacci sequence. So this is 1 plus fk minus 1 over fk. And assuming that the limit existed, this would tend to 1 plus 1 over L. So if it has a limit, it needs to be a value of L such that L is equal to 1 plus 1 over L, which is the same thing as one of the solutions to L squared equals L plus 1. So L squared minus L minus 1, which is exactly the polynomial that we got when we took the... That's exactly this, except with L plugged in, when we took the characteristic polynomial of this matrix, this one. Okay, so like all these like sort of pop math articles about like the golden ratio appearing all over the place, it's really because the real reason is because it's related to this matrix. That's what I would say anyway. And this is like a very simple matrix. There's lots of times when this matrix actually does govern some kind of behavior. And so the eigenvalues of this matrix matter, and the largest eigenvalue is the golden ratio. That's really the reason why the golden ratio appears all over the place. Okay, anyway, this was hopefully an example that would motivate the fact that understanding some linear algebra can have really powerful consequences. And you can uncover something real, you can uncover some real understanding that you didn't have before. Sorry, my camera cut out there for a second. I'll try to smooth it in editing, so maybe you won't know what I'm talking about. But I fixed the camera, and I was just saying that you can get this limit using calculus, right? So even after you'd taken calculus, you could sort of prove that the limit would have to be the golden ratio. But now we see another linear algebra reason why. Right? The point is that as k tends to infinity, we approach some multiple of the first eigenvector. Right? And what is the first eigenvector? The first eigenvector, let me add a page. So as k tends to infinity, we approach some multiple, some alpha times the first eigenvector. Right? Forget what alpha is for a second. So this is alpha times lambda 1 comma 1. What does this say? Well, this is supposed to be given by, right, fk plus 1 over fk. So what this is saying is that the next term in the sequence should be roughly lambda 1 times the previous term in the sequence. In other words, they should be going up by a ratio of roughly lambda 1, which is the golden ratio. Okay, yet another way to see it, by the way, is we said that it's roughly, fk is roughly lambda 1 to the k over lambda 1 minus lambda 2, which means fk plus 1 is roughly lambda 1 to the k plus 1 over lambda 1 minus lambda 2, which again is roughly lambda 1 times as large as fk. So there's three different ways to understand why the golden ratio is appearing. One, you could solve it using calculus, essentially. Assume it has a limit, then its limit has to be one of the roots of L squared minus L minus 1. That's one way to see it. The other way to see it from a linear algebra point of view is, well, the long-term behavior is governed by the largest eigenvector. Sorry, the eigenvector associated to the largest eigenvalue. And the largest eigenvector the eigenvector associated to the largest eigenvalue is basically lambda 1 over 1. In other words, the first component should be roughly lambda 1 times as big as the second component. In other words, the ratio of consecutive Fibonacci numbers should be roughly lambda 1, which is the golden ratio Or another way to say it is, once we've understood the behavior in terms of the linear algebra, then we know that the terms are roughly lambda 1 to the k over some constant, some fixed constant, which means that as you go, you're multiplying by roughly lambda 1 every time. Okay, so the golden ratio does not appear by accident. And hopefully what this lecture was supposed to motivate was there are times when it's not obvious that linear algebra should yield anything useful. I think at the beginning, when we started talking about the Fibonacci sequence, I would say that introducing this matrix and these vectors maybe wasn't so intuitive. Why should we do this? But the eigenvalues and the eigenvectors of this matrix, which controls the growth of the Fibonacci sequence, tells you an unbelievable, deep amount of information about the sequence. And in fact, we'll see in the next lecture, when did I start talking about this general setting? This general setting where you have some state vector that transitions according to some matrix. You can understand the states using linear algebra on the matrix. And this indeed is actually, in some ways, this is the whole idea behind Google PageRank, which, if you remember that quote on the syllabus about the founders of Google computing the Perron-Frobenius eigenvector of the web graph and becoming billionaires, it's because they understand some matrix and how to get really valuable information out of a matrix by understanding its eigenvalues and its eigenvectors. Okay, so fun stuff coming up ahead. I thought today's lecture was fun, but maybe you didn't. But the next couple of lectures where we're talking about Markov processes and Google PageRank will again be another example, a really striking example of how knowing linear algebra can tell you some really very deep and powerful information. All right, something to look forward to. So I'll see you in the next one.